So I can do that. I can do. I guess that's better. That's better. Okay, are you ready? AV team. Okay, so I'll recap this in class, but because we're down 2 weeks because of the 7-year cycle plus the scheduling office missing a day wrong, we're supposed to be plus or minus 1 class, but not 2 classes. We made up the networking class as the recitation, and then the machine class is a really important one, but we don't have a separate week for it. So we're going to overlay it in a few weeks. So today, Nadya is going to introduce modular machine building. Wednesday will be output devices that includes the crucial topic of motor control. Then next week, we don't have a regular class because of Veterans Day, but we do have the recitation, and that's going to be on machine building components. And then I'll go over this in class Wednesday. What we want to do is a group project. So each of the labs has some version of a robot available, and Nadya has these machine building components. And what we want you to do is a group machine building project, which doesn't mean developing the stuff from scratch, but it means integrating the parts into something that does something. And every year it's a really fun exercise to take a few degrees of freedom and make it do a task. And then we'll go through those during the last week of the semester, and then the final projects during the final exam. Okay? So Nadya's going to introduce machine building, and then in particular she's going to introduce the modular machine building components that will be available in each of the sections to use. Then she's available this week, traveling the week after that, and then back the week after that again. And so she's going to cycle through each of the sections to help you get started with the modular machines. Okay?
So we're going to talk about machine building today. We're going to start with...
So can you pause the machine that's competing with you?
Is it?
It's a little noisy.
Okay, so you guys have all used this machine by now, right? No? Yes? Yes. And it's like a small version of a much bigger machine. Hold on, my computer is having I/O issues lately. What is the largest machine any of you guys have used for milling? I'm just going to do this. You guys can have a preview on the side. It would be great. Anyone? The Shopbot is the biggest machine you've ever used.
Yeah.
If you compare the Shopbot to the Modelo, what are the biggest differences besides size that you might encounter?
Access freedom.
Sorry?
Access and freedom.
Sorry?
Like the number of freedom access.
Yeah, but they're the same for the Mandela and the Shopbot, right?
Oh, yeah.
Size of material that you can build.
Sure.
Accuracy?
Accuracy, yeah. So the accuracy is different. Why is the accuracy different?
Tool is smaller.
The tool is smaller? You can put a tiny tool in the Shopbot though. So why else is it not as accurate?
And when you work with larger work pieces, you don't care that much about how much.
What if you do care? So, sorry? The thread pitch? Yeah, in fact, the Shopbot desktop uses a ball screw, so there's threads on it. But the Shopbot regular Shopbot PRS Alpha, what's its drivetrain? Rack and pinions. Don't worry, I'll tell you what rack and pinions is in a second. So if we look at all of these machines that we have access to right now, here's an industrial robot arm, the one that's at architecture, right? And it's set up to be 3D printing, and it can 3D print, but it has all this like and it's configured so that you can put whatever end effector you want on the end of it, right? But there's actually quite a lot of work that you have to do to be able to do it. And at the end of the day, even though you have lots of degrees of freedom that you can move around with, it's kind of floppy because the structure is big. So not only is the drivetrain less precise, but the thing that Alex Loca makes people do when they take precision machine design is like push your fingers together like this and then try to move them apart and try to move them around. You can still maintain a very tight tolerance within your two fingers, as opposed to like pushing your arms together like this and then trying to keep your hands in the same place. So this is a small structural loop where, say this is my workpiece and this is my end effector, making sure that this stays in position is much easier than making sure this stays in position. And so with the robot arm, you're kind of hanging out here, and even though you have all this movement that you can do, which is cool because then you can do complex things, you have a very large structural loop. So why is 3D printing not as, why can you 3D print with something that's kind of more floppy like that as opposed to milling? Why do you think that there's such a proliferation of 3D printers? What kind of force does a 3D printer encounter when it's making something?
Fairly minimal, it's just a lot of extruding.
It just has to extrude, right? So it doesn't have to push against anything. Or if it does have to push against something, something is very wrong. And so building a 3D printer means that the mechanical system that you need to move your end effector around with doesn't actually have to be that strong. What about milling? What about milling with the Modella? Does that have to be really strong? No, yes, no, not really. Why not? So-so. Well, as opposed to, for example, if we were going to mill with the 5-axis Herco mill, does that have to be strong? Kind of, but it also depends on what you're milling, right? If you're milling foam, you're not going to encounter a lot of cutting force, whereas if you're milling metal, you are going to encounter a lot of cutting force. If you want to mill metal as fast as possible, you're going to encounter tons of cutting force. And so lots of people have thought very hard about how they can move as fast as possible with these kinds of machines. But that's mostly because they're thinking in a fabrication environment where throughput is critical, right? So if you want to mill as many parts as fast as possible, then optimizing cutting force within the capability of your machine for maximum output is really crucial. Although in your case, I would recommend trying to minimize the number of end mills that you break. So, there are many different kinds of personal fabrication machines now. For example, Glowforge just came out with a $2,000 laser cutter. There's lots and lots of these 3D printers. There's lots and lots of different kinds of desktop mills that you can control in different ways. But what if you wanted to make something like a little bit more personal? It was my birthday on Saturday, and I wanted to show you guys this video that my collaborator James made for me. So here we have a toolpath. Happy birthday, Pico, that's what he calls me. And then it is attached to this single axis through your freedom and another single axis through your freedom. And he baked this cake. And now there is a frosting extruder that is extruding frosting into the cake. Pretty cool. If we skip ahead though a bit in the video, you will see that actually the cake doesn't look, well, the cake's beautiful. It's just like me. So if you wanted that to be as easy as possible so that your precision perhaps could go more into the refinement of the cake and less into the making of the machine, how can we make it as easy as possible to prototype these kinds of machines? So the example of, oh hey, I have 100 cakes that I want to decorate in exactly the same way. At what point is it going to be easier for you to make a machine that does that as opposed to just decorating 100 cakes by hand? For James, maybe it's going to take a while. But so the Machines That Make project has been continuing throughout how to make almost anything and how to make something that makes almost anything, which is the class that is taught once every 4 years as kind of conjoined with how to make almost anything, where you make all of these different kinds of machines. And so to be able to think about machine building, I'm going to break it down into these different layers in this pyramid. So first of all, we have a tool head, right? So if you want to automate something, there's some process that you want to automate. For example, lasing something, or milling something, or cutting something, or moving M&Ms around. And so everything is kind of subservient to that tool head. And the tool head rests on some mechanical system. And like we're kind of talking about with the shop lots and the modellas, the mechanical system kind of depends on what tool head you're using. And then the mechanical system that constrains the motion of the tool head has to be driven by something. What could it be driven by, for example?
Sensors and actuators.
But what are those? Motors, hydraulics. And the sensors would be if you wanted to have feedback in your motion system. So for example, you could just say move here, and hopefully your machine would move there, but if it encountered some kind of problem, then a sensor might help you in doing closed loop positioning and increasing the accuracy of your machine. And to be able to control those sensors and have their feedback do something to their actuators, you need to have a control system. And the control system might just say, move to this position, or your control system might be slightly more complicated. Like you might say, if this thing turns pink, then shake it a lot, or something. And then for applications and interfaces, you might have just the kind of thing that you use already with the fab modules. Or maybe you want to have a kind of application or interface that is totally different. Like you want people to walk up to your machine and yell at it and have it produce something. That would require a totally different kind of interface. And those are all different kind of layers of things that you might be working on. They're all well-established fields. But it seems like in machine design, the most difficult thing is the system integration between all of these. It always seems like somebody will be very skilled in one of these layers, but not necessarily in executing all of the things together in one system. So the main thing that we want you to learn with machine building, the machine building project, is how can you synthesize all of the things that you're learning in how to make almost anything from these different parts into one working system. And so it doesn't only have to do with the machine itself. The machine has to do something useful, and so that useful thing could be described by your CAD model, which you then convert into some kind of machine instruction. And so another portion of machine designing is also how do you take the model, which is the thing that you want, and turn it into something that your machine can understand in terms of instructions. And so the most common way for that to happen is in G code, but there are other ways as well, which I'll get into in a second. What is this? Yes. It's a laser cutter. And sometimes when people are like, oh, I need to buy a thing, they're like, oh, I need to buy a laser cutter. And you're like, okay, yeah, buy the laser cutter. But actually, the two things on the side of the laser cutter here are pretty crucial. One of them is the air filtration system, pretty useful because laser cutter's kind of stinky, and the computer. And the computer controls the laser cutter. So in a way, you have the computer is integral to the functioning of the machine. You can't run it without the computer that has the print driver installed. Well, it's kind of more obvious with this OMAX water jet. Like the OMAX water jet as a machine is very cool, but then the computer's kind of tacked on as like this afterthought or this side thing. And so I design something on my computer, and then I maybe create the CAM file already, and then I bring it to this other computer, and the only function that this other computer has is to run the code that I brought to it. It's kind of a roundabout way of doing things. And so one of the things we're trying to do with the fab modules is to make this easier by doing the tool pathing and the running from the same interface. And maybe you guys just think the fab modules are like this slightly annoying, not very easily to debug way that we're using machines here. But actually, if you look past that a little bit, then it's actually quite an unconventional approach to how you might use digital fabrication tools. Because right now, digital fabrication tools are typically employed in large organizations where one person is dedicated to the running of that particular tool. And as they get cheaper, more people can have access to them. But there isn't a whole lot of work being done in making sure that those interfaces are universally addressable by people who might be well-versed in lots of different kinds of fabrication techniques. And so, same thing with tool pathing. Like, yes, fab modules might be limited in their tool pathing capability, but other tool pathing software is still, let's say, pretty tedious. And so, how does tool pathing software work? You have to translate something that is within the coordinate space of your machine. You have to somehow translate it to the coordinate space of your actuators. which is easy if you're just doing stuff in three axes, right? So you're like, if I move my actuator this way, then my end effector is also going to move this way. But there are ways in which, for example, if you moved a robot shoulder, then the position of the robot elbow is going to depend on the position of the robot shoulder. And so figuring out how to get your end effector to the right place means that you have many dependencies in all of the different joints, and it gets slightly more complicated. And so full 5-axis toolpath planning for making all kinds of complex surfaces that people in, for example, architecture seem to like, gets complex. And so you need to have something that translates coordinates in your part system to motions by your machine. And this is traditionally done by G-code. I hate G-code. G-code is like a very, very archaic way, as far as I'm concerned, for controlling machines, because it means you can't include other kinds. It's not an extensible programming language, right? It's just move your machine to this and that position. So if you wanted to add something like temperature on or take a picture at this position, you'd have to kind of like hack it. You'd have to kind of hack G-code to do something that it wasn't intended to do. And so in terms of the control system that you're interfacing with, it seems kind of silly to me to take a powerful computer and create a instruction set for your machine and then take it to another computer, which then reinterprets it into motion for your motors, as opposed to controlling the motors directly. And so in this case, there's like a conversion that takes place. Where you have, there's a lot of other things that happen in your machine, right? If you don't have something that interprets your G code, then you can never have something like look ahead, where if you were going to do, so even if you're going to do a straight line with a laser cutter, you can't start at top speed and end at top speed, right? You have to like start, so your machine will always make a noise like, and while it's doing that, it's going to be going slower in the beginning, faster in the middle, and slower at the end. So you have to pulse the laser accordingly so that you don't like burn all the corners of your parts. So if you look at really old laser cut parts, by the way, you can see that all the corners are burnt for that reason. And so in the shop up, for example, there's something that does all of that interpretation for you. It takes the G-code coordinates and it figures out the acceleration profiles that it can use, and it figures out smoothing and all these other things. And so you not only have the computer, which is there in the background, which is streaming the G-code to this computer, you have this computer too. So you have all of this stuff that's kind of multiplied. And so our preferred approach is a machine-controlled network where you just add computation as is required as your machine gets bigger and bigger, which is what we're going to go into in a second with the network control system that you guys can use for this assignment if you feel so inclined. All right, so moving things. This is a rack and pinion. This is a lead screw. This is a timing belt. What machine that you guys use regularly uses timing belts?
Cars.
Like cars?
Scanners.
Bikes. You have a fancy bike. I meant more like in how to make almost anything.
3D printer.
3D printers often have timing belts. What else? The laser cutter has timing belts. What do 3D printers and laser cutters have in common?
3 axis. No.
3-axis motion.
They have a head that feeds either, shooting a laser or shooting stuff.
So it's like a head that shoots stuff.
No force from the workpiece.
And so there's no force from the workpiece. So the heads don't really make contact with anything. And so the timing belt, as you might imagine, kind of stretches. And so if you had something with cutting force, then the timing belt, every time it has to change direction, stretches a bit. And that amount of stretch, so if I'm like going this way and then I decide to go back that way, the amount of delay that there is, or the kind of that gap, is called backlash. Backlash is annoying, and so that's why a lot of other machines don't use timing belts, because backlash can be a huge problem if you're trying to get accurate milling jobs done. However, what is a drawback to a lead screw? If it's so much more accurate, why don't we use them all the time? They're slower. Why are they slower?
Because converting one rotational to a linear direction.
We're kind of doing that with the timing belt too, right?
Like the threads are really close together.
The threads are really close together. That is a good point. So for example, if you look at a lead screw, regular screws that you use for screwing wood together, they'll have like one helix that goes like this. So you turn once and it goes one pitch distance. And lead screws can have multiple starts. So kind of like DNA, they could have two that are intertwined, so that if you turn one full rotation, you move 2 pitches instead of 1. Or you could have up to, like the most I've ever seen is 16 starts. And so then with one rotation, you move 16 pitches. So that's one way of making lead screws faster. So that your motor, because the amount your motor turns with the timing belt can be geared so that you move really far with only one rotation. And so to approximate that with a lead screw, you can make more and more complex lead screws. So lead screws could be fast if they're really, really expensive. Then if you have created motion with these drivetrains, so you have motors that are moving things around, how do you constrain the motion to the direction that you want to be going in? How does a shop-out, for example, do it, the large shop-out? There's like a V on the edge, and then there are these like bearings that sit on it, and then it rolls along that. So there's like a groove and a V groove that makes sure that it doesn't wobble in this direction. It could go up and down though. Why doesn't it? Well, if you're milling something so hard that it's lifting up the entire shop-out gantry, we've got bigger problems. That's why. And so for every single kind of end effector, you're going to have a very different kind of drivetrain that is going to be optimal. And so if you're ever bored and on the internet, I encourage you to look at high-speed video of cutting tools milling things, because it's awesome. And you'll see how much force is required for doing something like this video is of cutting metal, which I will not show you right now for the interest of time. And then if you want to restrict linear motion, then V-grooves are good and they're relatively low cost. But if you look on McMaster-Carr for all of the different kinds of guides that you could use for linear motion, you'll find that there's lots and lots of options, including slide rails and guide shafts and different ways of constraining things. And basically, the more precise they are, the more expensive they get, typically. And there are clever ways to make sure that you don't need to have as much precision. Well, what's the biggest problem that you can imagine if you had 2 guide shafts that are like this, and you needed to move something on back and forth on them? You can't imagine any problems that you might encounter? Maybe it got stuck. Why would it get stuck?
They're not parallel.
They're not parallel. And so maybe the guide shafts are not parallel, or maybe the holes that you made that are riding on the guide shaft are not parallel, right? And so if they're both not parallel in the same way, it kind of doesn't matter. And so it's not just that you have to make them as precise, as exactly parallel as possible. You have to make them as close together as possible. And the best way that people generally do that is they try to make them as precise as possible, and that results in them being as parallel as possible. But there are clever ways that you could get around that. For example, you could put your guide shafts in position first, and then put your stage on it, kind of loose, and then glue them in place. Or, for example, in this machine, which we used to have everyone make in how to make almost anything, the guide shafts have these flexures in it, where we would assemble the whole thing first, and then we would move this over to the side and heat this up with a heat gun so that the plastic would deform, and then we let it cool off and relax again, and then we do the same thing on the other side, so that the guide shafts better approximated the bearings. And so to minimize the amount of wear on your bearings, you can do lots of clever things like that. And you can buy fancier and fancier bearings. But the key is to not over-constrain your motion by adding too many surfaces that are in contact with each other. That was this part. So, kinematics. What are serial kinematics? Who's a mechanical engineer? Nobody. Wait, Camille. So serial kinematics is if you move X, X moves and no other axes move. If you move Y, Y moves and no other axes moves. Whereas parallel kinematics are you move like A, and then that also affects the coordinates of B, for example. But when we look at most machines that you guys have access to in the shop, they have serial kinematics. And it is only slightly more complicated to control machines with parallel kinematics. Like an example of a machine with parallel kinematics would be you're hanging something from two strings. And so as you vary the length of the two strings, the thing is going to be hanging all over this space. But the amount of string that you let out is going to both vary the height where it's at and the and where it is in horizontal space. Because so you have to kind of you have to do a slightly more complicated calculation to figure out how to get your end effector in the right place. So here we look at the shop on desktop. It has serial kinematics. It has a drivetrain that we've already discussed. It has a spindle. And then if you look at the Ultimaker, for example, does it have serial or parallel kinematics? Serial, yes. It kind of looks more complex because it has these crossed guide shafts, but at the end you can see that there is one motor that controls X, one motor that controls Y, and one lead screw in the back that controls Z. Okay, so that is all right now, at least, on the background of machines and machine design. And in class, Neil is going to cover much more about machines and machine design. And so the assignment is that every section has to make a machine, right? And so the problems that we used to have was we used to have everyone make that machine, well, a slightly different version of that machine. And the trouble was that it never worked. And so this is like from someone's How to Make Almost Anything page, and it said, I spent most of my time preparing for the final project, so that's why this machine didn't work. And so we realized that building a machine was taking too long, and also that the machine was maybe too specific to be interesting to the breadth of students that apply to How to Make Almost Anything. And so our strategy here is that we're going to remove lots of the, like, that's a 6 minimum, depends if you use the on-sort or the shop on, but it's like maybe a several hour milling job, and it involves quite a lot of assembly, so we're trying to make it much, much faster. And so, for example, if we take as an example decorating a cake, and we need 2.5 degrees of freedom. Yes?
Just maybe like a general question, how would you define a machine just generally?
Something that does something.
So, okay, so the definition could be pretty broad then.
Yeah. I think that for the purposes of the assignment, we want you to do something with software, something with embedded software, and something with mechanics, and something with an end effector. And so we are going to try to make it as easy as possible for you so that you only really, I mean, unless you wanted to build, you can design, you can do as much work as you want, obviously. But for the purposes of this assignment, we want you to take a tool head and make your own applications and interface, and otherwise the control system and the motors and the mechanical system, we have this cardboard version that you can take advantage of in building your machines. So I'll show you another video real quick. This one. So this is James, the person who made the cake. And these are, when we first started making these reconfigurable axes where you could decompose the degrees of freedom that you might have in a machine into these individual axes. And so each one has its own little control node. And I'll show you in a second the library that controls it all. And in this case, it is configured to be a, it's configured to be a 4-axis hot wire cutter. what can you do with 4 axes that you can't do with 3?
Okay.
This? This? Yeah, you could cut like a circle on one side and a square on the other side. But in this case, it's just one extrusion light testing. And so the idea is that by configuring these axes in lots of different ways, you could easily prototype lots of different kinds of motion. Like so. And so I brought also a rotary axis, which I don't have a cardboard version of right now. But you can imagine that together, so these are two aluminum versions of it, that with this you can go back and forth and move around. That's helpful. This is, by the way, another parallel kinematic stage. It's like a kinematic model that's a lot like an H-bot that was designed by Alon Moyer, where if you move them opposed, you move in Y, and if you move them together, you move in X. So that is parallel kinematics. And with all of these different machine building blocks, you could easily create the motion system for the end effector that you might have in mind without having to think too hard about it. Here's another hot wire cutter that we made. But then for now, we want you to build these cardboard machines. And that is a lot easier than building the plastic milling machine. You start with trifold cardboard that is used for science fairs, you know, like the poster board. And so we like to say that you start with science. And then, here, I'll show you another video that explains construction. Can you make something that is a machine that is more precise with a machine that is less precise? Who thinks yes? Who thinks no? Huh. You. If we couldn't make more precise machines, then we wouldn't really be able to, why would we be, how would we be making progress here? So, you can make more precise machines.
How?
Well, you can do clever things with constraining motion. So you have, these are all people that have done this assignment, by the way, in Fab Academy, which is a global version of this class. So you can see things that you could do that are useful. So for example, if you take the shotbot and you mill a flexure in it, then the flexure is an error-correcting way of assembling something. And so if you assembled something like this machine, then in that machine you already have kind of a tighter tolerance than the shotbot does itself. And then if you made it into a milling machine, you could make smaller parts than you would be able to with the shotbot. Lots of people made hot wire cutters, probably because that was in the video. Also plotters, because that was the example code. But lathe, ketchup extrusion, cocktail mixing, and so you can see that for a lot of people, adding an extra degree of freedom where for example, they do a rotate. This is a zucchini cutter. They couldn't attach the knife to the machine well. They did all the other parts well. So you can see, it makes it easier. So here, for example, you're adding a rotational degree of freedom to your machine, which would otherwise, and not necessarily making the rest of the machine a whole lot more complicated. So that this is dripping bleach on textiles for kind of textile printing. And then there are also, this is like signaling. And there are also not only one sand gardening robot, but 2 sand gardening machines. You can see you make very silly things when machine building gets really easy. Cave decoration, sand gardening. So the plans for all of that are on mtm.cba.mt.edu. If you go to this one, modular machines that make, you can see this is the Rhino model for the cardboard. It's cut for the science that you can get at Office Depot, but if you change the Rhino model for whatever thickness of cardboard or whatever you have, then you can adjust it to accommodate different thicknesses and also different lengths of these aluminum tubes, which we're using as the guide shafts. It has Delrin bearings in it, which I'll give you if you guys want to be using them. And then has some recommendations for how to laser cut. And then also links to how to use the software. And we also have another spot for documentation here, which has more spiffy videos that load slower. That has a lot more also about how you might plug everything in and how the wiring works. So the way it works is there is a Gestalt node, which I will lend you guys.
What's Gestalt?
Gestalt is a library for controlling machines, which you can get to at github.com/Nadya/PyGestalt. And if I go to that repository, there is a examples folder in which there are machines and nodes. And so if you go to the machines examples, then let's look at how to make almost anything. And for example, let's look at a machine that controls one node. Oh, whoops, I didn't mean that. I meant to look at it. So this library you start with the interface between your network of machine nodes and your machine, which is done over RS-485. So it has a cable that's like the FTDI cables that you have been using already. This one. Which is connected to a board, which is connected to this board, the FabNet USB board, where you add power supply. And so the power supply is going to depend on what motors you have connected. So if you have motors that need 30 volts, don't connect a 5-volt power supply. But there is a large voltage regulator on the logic boards that will regulate between, check the data sheet for exactly what it regulates. But I think about 50 volts and needs about between 6 and 50 volts, so any power supply that you have. And then the Gestalt nodes themselves are daisy chained to however many nodes you need on your network. And these are all stepper motor boards. I have preliminary designs for other boards that will control, for example, servos or DC motors, but for the purposes of the class, use stepper motors for now. And this, in this schematic diagram, this is the RS-485 communication micro. This is the microcontroller, and this is the stepper motor driver. And so if the stepper motor driver is rated up to 2 amps, and so if your motor needs more than that, don't use it. And so if we look at this example code again, here we have the specification of what serial interface we're using. So here we have the port name USB 0, which is the case if you're using Linux, for example. But if you're using a Mac, then it's going to be some really long string that you have to look up. Are you guys all familiar with that? Who uses Macs? And so if you plug something into the serial, how do you look up what it is? You can press, so You can say ls, or here. You can say ls dev tty star. And so here you can see I have USB 0 as a 0 port that shows up. But on a Mac, something else would show up. It would be like USB 86, whatever. It would be a long string, and just copy that and put that in the code. What about Windows users? Who uses Windows? So then it's like COM1 or COM2 or COM whatever. So you just have to look which one shows up when you plug it in, and use that one when you're running the code. Okay, so we have, in this controller, we have one node, which is an x-axis node, and it uses this Python file to call functions on that node, which you can ignore. And you can see that here in the initialization of the kinematics, what we have is a board that microsteps. What's microstepping?
We haven't done that yet.
Oh, right. Output devices, next week. You will learn that in a stepper motor, you can do a full step, or you can oscillate between two full steps and things that are called microsteps. So your motor is kind of in between two full steps. So there's 4 microsteps, which makes your stepper motor a little more precise. And then the elements stepper forward, it means that the total amount of degrees that your stepper motor moves in one step is 1.8, which is fairly standard. 0.9 is also fairly standard. And the pitch of the lead screw, in this case, is actually the pitch of the lead screw in this case is actually 2. But because this is this motor has 4 starts in its lead screw. So what did that mean again? It means this.
Travels 4 times as far for one rotation.
Yeah, so if I move the motor 1 full rotation, it moves 8 millimeters, because each one of these threads is 2 millimeters wide, and there's 4 of them. If you buy, the previous pitch is the pitch of a 1/4-inch lead screw if you convert it into millimeters. And so now I have the kinematics of this element all already written up in this library, so that when I then have these functions that I initialize here, so for example, move, I pass the kinematics of my stage, and instead of having to say, please step 5 degrees and having to figure out how much that means in some other computer that's somewhere else, I can just say move 1 millimeter, and it will figure out using the kinematics what it has to do to be able to move 1 millimeter. So if I would change here the elements to be, instead of a lead screw element, I made this a timing belt element, and there was a gear ratio for the timing belt pulley, it would also do the correct calculation there. So most of this you can ignore if you're going to be using it, except that if you have more than one axis, you're going to have to add more axes to your file. So for example, in the XY plotter, I have 2 nodes. So you can see I have 2 leads. I have an x-axis and a y-axis, both of which are the same. They both have stepper motors, and I have direct drive on both of them. And so if I were to add a z-axis, because I wanted to do 3-axis control, you could see that it is fairly trivial to add another node and then create a new compound node that has the x-axis, the y-axis, and the z-axis, and create new moves that stream to that. Right? Right. Okay.
Oh yeah, sorry. Can we make a compound mode with the XY node and the z-axis, or we have to write x, y, and z?
You can make a compound node name whatever you want, and you can put whatever you want in it. So you could have like a compound mode with the x, y, and then you could have a single node with the z, and then you could have another compound mode that had the compound node x, y in it and z. But it would probably be simpler if you had 3 nodes, and then you made 1 compound node that's x, y, z. The only reason that you might want to have 1 compound node and 1 separate node is, for example, there's a part of this library that could control other machines, like if you had a KUKA robot arm, and it talks KUKA robot language, and you wanted to put and you wanted to put like something underneath, a stage underneath the robot arm that moved back and forth in unison with it, then you could have one compound node, which is the Cougar robot arm, which has to talk its own Cougar whatever, and then one separate node that is moving like this. And you might want to do a check to make sure that the compound node has finished executing before you send another combined packet to both motion systems. So it's supposed to be for versatility. So this is like the class of machine that you're instantiating, and so if you run this file directly from the terminal, you can it'll execute this part of this script. And so here I'm generating a virtual machine now, which is called stages, with the persistence file test.bmp. I'll just delete that. And so when I run it, it creates a new virtual machine persistence file if one isn't already found. And it sets a velocity request. The velocity request is kind of arbitrary right now, but let's say that this is an approximation of 8 millimeters a second. And then here I just have a demo where I'm making it move back and forth 7,000 times. And so for each move in that list of moves back and forth, it's going to check to see that the move is completed, and when it's done, it's going to move the next move in the list of moves. So what's going to happen when I run this? Well, there's no persistence file, right? Because I just deleted it. So I'm going to have to make a new persistence file, which is the thing that says which is which axis. And so I have to identify the x-axis, which is done by pressing the button. And then I have to identify the y-axis, which is also done by pressing the button. And then it will move around. So now it's moving around. Hopefully your machines will do something more interesting than just moving back and forth. But this would already be great. And if you want to see what, for example, people did last year, this is a documentation page for that. Well, maybe the internet doesn't want to talk to me. I crashed it. Okay, I blame HTML5. But you can look at this. It's linked to from mtm.cba.mit.edu. And so I would recommend that you get together, or that you try to coordinate somehow with the rest of your section to tell each other when would be the best time. Sometime this week, maybe even earlier this week would be better than later this week, for me to come by and help you guys assemble these and get started with it, so that you can start figuring out your end effectors and what application you want to work on. And then what worked pretty well last year for some of the sections where they appointed someone who was supposed to be like the program manager-ish person and got other people to do things on the project, you could decide that if that was appropriate for your section on your own.
Will you be able to come to class Wednesday?
And I will be in class on Wednesday.
Okay, so during the class I'll cover output devices, but towards the end what we could do is a collective scheduling in each of the sections.
Yeah.
So maybe with everybody gathered you could do it. But to go through, so Gestalt grew out of Alain Moyer, who's a very interesting machine builder Nadya works with, taking one of the first machine building classes, leading to this notion of, instead of sending a file to the machine, make machine networks. It's towards the end of life in that Nadya's thesis is what's going to come after Gestalt, where the goal is the lines of Python code there have nothing to do they describe what's happening here, but the representation have nothing to do with what's happening here. And so what she's developing is ways to align the description of the machine with the construction of the machine. And so that's what's going to come after Gestalt. But for that, come back for her thesis. And so each of the labs will get kits of motors, motor controllers, Gestalt networks, and these starting trifold construction systems. And the idea is you can assemble something that does something as an exercise in putting together all the parts of the machine. Okay?
So what this machine actually is, that I saved from last year, is something that like moves a laser around for laser light shows. So here it's painting the Ghostbusters logo. Here's Dan.
Yes.
Machine building is so fun. There was also a magical chess playing machine box that was made by Architecture last year.
Do you have a video of that? That was very cool. Yeah.
So it's magnetically moving the parts back around on the table. Someone wrote the chess playing app for it. Neil's the king. I'm the king. This is a painting robot. So you can see they made like an extra component for it. And Harvard used a lot of clips. Harvard made a light painting machine. So yeah, I think that the things that worked well were where you tried to do a lot of integration between what you wanted the machine to do and how you interface with it. So I thought it was very cool that you could play the chess game on a tablet and it would actually move the machine that you were using, as opposed to you having to like script a bunch of things and then it moving around like I'm demoing right now. Something much cooler than this would be cool.
Okay.
Yeah, that's it.
So again, Wednesday I'll talk about a lot of output devices, but I'll cover motor control. And then the week after that, I'll cover machine building parts. But you can get started right away. So after today's class, start thinking about it. And then I'll leave time at the end Wednesday for Nadya to meet with each of the sections to plan when she's in residence. Okay, questions? A little louder.
Will there be individual?
Actually, can you put this to sleep now? Will there be what?
Will there be individual projects for output devices in addition to this?
Yeah. So the machine building isn't due in 1 week. It's going to be at the end of the year. There's going to be the individual output device, which is you're going to interface a processor to an output device and make it do something. To understand the machine building, in some years we did from scratch machine building, and that was too much work. That was like 2 final projects. In some years we didn't do it at all, and that left a void, which is not exposure to it. And so what you're doing is going to be easy in that you're starting from pre-made components, you just need to put them together. But it's a small chance to work together as a group on something with pre-made components. But you won't be presenting them until the end of the year. Okay? And so the minimum is just take Nadya's parts, make them together, and move, and you're done. But it's more fun than that. You'll likely go beyond that. Okay? Yeah.
Just to confirm, we do that part as a group.
That's unlike the other reason I like this is unlike all the other things. You're such an interesting group. That's one you can do as one group, or you can be more than one group. But that's not an individual. That's a collective project. Anything else?
But when you guys present your machines, which they're going to do on the...
So if you go back to the schedule.
So when would it actually be?
Yeah. So the sequence is output devices. The assignment is going to be interface a processor to something that makes an output, which could be a motor, it could be a light, it could be a speaker. There isn't a new assignment the week after that. The week after that, we don't have the regular class, but the recitation I'll go over machine building components. Input devices, you'll measure something as an input with a sensor. Interface week, you're at Thanksgiving, and that's build a desktop interface to something you made, and that's on programming tools. And then composites will be laying up a composite. Then the last regular class meeting is when you'll show what you did on the machine building projects as a group. And then the final exam is when you show your individual projects, but we also have the open house, so you'll bring your collective machines then.
And so for when you guys present your machines, you'll present together as groups, and then we'll ask some questions about who did what, so that we know who contributed what to the project. But it's not expected that everybody does all parts, but it is expected that everybody does some parts.
Well, in fact, the opposite for this one is that you can layer, unlike the final project where you have to show master of everything here, one person can do mechanism, one can do motion control, one can do application development, and you stack all of those up into a project. And one of the goals is it's a chance to work together that way.
And that's going to be on December.
And then on the 9th is when you'll present them in that class.
And then the project on the 15th is, that's the individual.
Right. Yeah. Okay.